General relativity, step by step. I've been considering the linearized Einstein field equations, and I was looking for solutions of this particular form here. And I was hoping to use the linearized Einstein field equation to pin down the undetermined components of this equation. We've got an A here and a 4-vector K. And what I did in the end was to come up with this rather beautiful, succinct relationship on K. So what does that mean? Well, let me write out what the solutions that we've got. We've got H bar mu nu. I'll pinch in a bit. H bar mu nu equals A mu nu. We still don't know anything about that. We'll pin that down later. E to the I K alpha X alpha. So what I'm going to do is I'm going to write my K alpha, because it's downstairs, it's going to be a minus omega Kx, Ky, Kz, 4 vector, 1, 2, 3, 4 terms. And I'm going to write my x in terms of a t, an x, a y and a z. So it's pretty plain that what we've got is a mu nu x of I times this term here minus omega t plus k dot x. Just observe in passing how this nice 4 vector here, this 4 vector has got this very nice decomposition into a time component and 3 space components, and it's just another indication of the power of special relativity to bring these two apparently unrelated things together into this nice equation here. So this tells us straight away that if minus omega t plus k dot x equals 0, let's just say, that's for the 0 component, then that tells us that omega t equals k dot x. And so, this, are these crests? Yeah, I guess they're crests, because we're considering cos x plus I sine x. So where cos x is 0, that's a crest. Okay, so it tells us that the crest of the wave obey this rule here, and of course the crest of the wave are perpendicular to k, which is quite nice. And that tells us that the speed of the wave equals which way around? It's omega over k, of course, omega over mod k, which is quite nice. And of course we can get the speed of the wave by looking at our constraint on k from the Einstein field equations, which tells me that, is it a plus or a minus? It's a minus omega squared plus k dot k. Actually, let's write it, yeah, plus k dot k equals 0. So that tells me that k dot k equals omega squared, and that tells me that mod k equals omega, I guess plus or minus omega. And so the speed of the wave there is omega over omega, which equals 1, equals speed of light. That's nice. So the Einstein field equations tell us that gravitational waves, we don't know very much about them overall. We haven't pinned down this A yet, we don't know what that is yet. But we do know that whatever these things are, they move at the speed of light. And I've been wondering for a long time, is that obvious? Well, no, it's not obvious. Well, it is obvious and it isn't obvious. It's not obvious in the sense that it took quite a lot of algebra to get there. But however, if you think about these gravitational waves in a slightly different way, you'll remember that the perturbation tensor, the pseudo-tensor I guess you call it, is Lorentz invariant, or it does the correct things under Lorentz invariance. And if the waves moved slower than the speed of light, that would say that they move at a finite speed, and that would say that I could catch them up. And that would say that if I got in my spaceship and caught these slow waves up, then I would be able to observe them in a steady form. They would be in steady form. They wouldn't move relative to me if I speeded up. So if the waves moved slower than the speed of light, then I could catch them up. and observe them at my leisure. Observe a steady perturbation tensor. Is that plausible physically? I'm not sure. No, it isn't. Well, the whole thing's crazy because they do move at the speed of light. What I'm wondering aloud is this obvious? And one consequence of them moving slower than the speed of light is that I can catch them up. And if I can catch them up, they're steady. And if they're steady, well, I don't... Maybe that is obvious. Oh, well, anyway. It's a counterfactual. I don't really know if it's sensible to pursue this line of reasoning. Anyway, so we've established that they move at the speed of light, and maybe that's obvious, maybe that's not. I'm not altogether sure. It's kind of sort of obvious, unless you think about it too deeply, in which case it becomes specifically non-obvious. Anyway, conclusion from this, the take-home message from this screencast. Gravitational waves move at the speed of light. Stop.